Hello, I am Matteo Martini from University of Genoa. Today, I present a joint work with Lorenzo Gerini, Giorgio Delzanno, Giovanna Guerrini, Fabio Solari, and Manuela Chessa, which is titled Immersive VR for the Assessment of Spatial Skills in Adolescents, Performance, Gender Effects, and Links to Computational Thinking. Spatial abilities refer to the skills that allows us to visualize objects, mentally rotate them, and understand how things relate to each other in space. Early adolescence is the period when these abilities consolidate and STEM trajectories begins to form, making it a particularly sensitive window for assessment. Y and colleagues showed that spatial ability is one of the strongest predictors of later STEM achievement. Importantly, spatial skills are trainable, and emerging work links spatial reasoning to computational thinking in young learners, the process of formulating problems and expressing their solution as logical step-by-step procedures that could be carried out by a computer. The validity of spatial assessment at this stage is therefore not just a psychometric concern. Inaccurate measurement can cause talent to be overlooked before educational and career pathways take shape. The two most widely used instruments to measure spatial ability are the mental rotation test, developed by Vanderberg and Kusi in 1978, and the pure spatial visualization test rotations, created by Guai in 1976 and later revised by Yoon in 2011. The mental rotation test presents participants with a three-dimensional target shape and asks them to identify, among four options, the two that are rotated version of that shape. Pure spatial visualization test rotations presents a reference object, a rotated version of it, and a second object. Participants must determine which of 5 options correctly applies the same rotation to the second object. Both instruments are extensively validated and widely used across STEM education research. However, being administered in paper and pencil format, they share the structural limitation of representing 3-dimensional content in a 2-dimension. Any 2D projection of a 3D object is inherently ambiguous. Depth cues are lost and occluded surfaces are invisible. Traditional paper and pencil tests make this worse by removing natural depth cues like shading, shadows, and perspective. This has real consequences for validity. Research shows that as angular disparity between objects increases, the task should become harder in a linear way, yet neither of the MRT nor the PSVT reproduced this expected pattern. Gender differences in mental rotation also tend to grow during adolescence, with female test takers systematically scoring less than males, and there is evidence that test design can amplify them, meaning observed disparities may partly reflect assessment artifacts rather than true ability differences. Immersive virtual reality might directly address these limitations. The Virtual Reality Mental Rotation Assessment, or VRMRA, is one of the first systematic efforts to translate traditional spatial tests into a fully 3-dimensional format. It adapts 12 items from the PSVT and 12 from the MRT into an immersive environment. Objects are rendered in 3 dimensions with realistic lighting and shadows. Participants can view objects from multiple angles, and hand tracking supports natural interaction. Validation with university students demonstrated that the VRMRA restores the theoretically expected relationship between rotation complexity and difficulty, a pattern absent in the 2-dimensional format. These considerations identify 3 interconnected gaps in the literature. First, traditional 2-dimensional assessments introduce construct-irrelevant variants that may distort ability estimates. Second, the format of these tests may contribute to observed gender disparities rather than reflecting true ability differences. Third, the relationship between spatial ability and computational thinking in early adolescence remains largely unexplored. This raises a central question. Can VR provide a more valid and equitable assessment of spatial ability? To assess these gaps, this study investigated 3 research questions. How does testing modality influence spatial performance in adolescence? Whether VR-based assessment reduces gender differences observed in traditional formats? And whether VR-based spatial measures show stronger associations with computational thinking performance. To address these questions, we designed an observational sequential study using a within-subjects design with 48 adolescents, aged 12 to 16, of whom 27 were male and 21 female. All participants completed the same sequential protocol comprising 5 phases. In the first phase, participants completed a 2-dimensional version of the VRMRA, administered on tablets and covering 12 PSVT items, namely the VRMRA Part 1, and 12 MRT items, or the VRMRA Part 2. We collected number of correct answers and completion time. They then attended 2 90-minute computational thinking training sessions using block-based coding on the EduBlocks platform, covering problem decomposition and algorithmic thinking. Participants had no prior formal coding instruction. This was followed by a computational thinking assessment consisting of 2 components, a problem decomposition task in which participants outlined the steps to solve a real-world problem describing their solution in natural language, and a Parsons problem, in which they built a working program by assembling printed pre-written code blocks based on a given problem decomposition. Each component was scored out of 50 points. The assessment was completed in 15 minutes, and the exercises were of similar difficulty to those used during the training. Finally, approximately 1 month later, participants completed the original VR MRA in Immersive VR on MetaQuest 3, using the same items in the same order as the two-dimensional version. For the VR assessment, we collected also head and hand motion tracking data. Moving on to the analysis of the collected data, the first result concerns overall performance across VR and 2D modalities. The plots show accuracy and completion time for each task type across the two conditions. VR improved performance in both tasks, but in different ways depending on the task type. For PSVT-style items marked as Part 1, accuracy did not differ significantly between conditions, while completion time decreased by approximately 100 seconds in VR, a significant 19% reduction. For MRT-style items marked as Part 2, completion time was comparable across modalities, while accuracy increased by an average of 1.3 correct items in VR, a significant 24% relative improvement. These differential effects suggest that the two tasks respond differently to the VR format. Stereoscopic depth and free viewpoint access appear to reduce perceptual ambiguity in the MRT, supporting accuracy gains. For the PSVTR, VR may streamline the mental transformation process, yielding faster responses without altering the final accuracy. Modality effects are therefore task-specific rather than uniformly beneficial. The effects of gender on performance depended on the task, and interestingly, the patterns went in opposite directions across our two assessments. For the MRT-style items, in the two-dimensional condition, males scored slightly higher than females, 6 correct items versus 4.95, which matches what's typically reported in the literature. But in VR, the pattern flipped. Females outperformed males, scoring 7.57 correct items compared to 6.33 for males. This was a substantial gain for females, about 2.6 more items with a large effect size and a statistically significant difference. Males, on the other hand, showed no notable change. For the PSVTR style items, the patterns reversed. Females had a slight edge in 2 dimensions, scoring 4.57 compared to 3.93 for males. In VR, however, males gained about 1.5 items with a very large effect size, while females showed no significant change. This created a male advantage in VR where none existed in the two-dimensional version. Overall, these results show that VR does not uniformly reduce gender differences. The new features of immersive assessment, like depth cues, physical movement, and multiple viewpoints, seem to interact with the spatial strategies used by each group differently. Research question 3 explored the relationship between spatial ability and computational thinking. Spatial ability showed statistically significant positive correlations with CT performance across both modalities. R equals to 0.5 for two-dimensional scores and R equals to 0.48 for VR scores. This confirms a spatial CT association in early adolescents at a developmental stage when both capacities are still consolidating. The hypothesis that VR-based scores will show stronger CT associations than two-dimensional scores was not supported at the aggregate level. However, gender-stratified analysis revealed a crossover pattern worth noting as an exploratory finding. For female participants, the spatial CT correlation was stronger in VR than in 2 dimensions, 0.56 versus 0.45, while the opposite held for males. Given the sample sizes involved, this pattern requires replication, but this is consistent with the interpretation that VR assessment may better capture spatial computational potential in individuals underestimated by traditional formats. 3 findings summarize this work. First, modality effects measurement outcomes in task-specific ways. VR improved MRT accuracy by 24% and reduced PSVTR completion time by 19%, with no significant cross-effects between tasks. This reveals that what a test measures depends in part on how it is administered. Second, gender effects are modality and task dependent. VR reduced the male advantage in MRT-style tasks, while simultaneously producing a female advantage in PSVTR-style tasks where none had existed. Therefore, VR seems to be not inherently equity-enhancing. Its effects depend on the interaction between task demands, affordances, and individual spatial processing strategies. Third, spatial ability correlates positively with computational thinking in adolescents, having R approximately equal to 0.5 across both modalities. This association is consistent with the hypothesis that spatial reasoning serves as a cognitive foundation for computational competence. VR-based scores showed stronger CT associations for female participants specifically, an exploratory result that warrants a follow-up. I will close by acknowledging the study's limitations and directions for future work. Our study has 3 main limitations. The sample of 48 participants from a single site, with more than half reporting intentions to pursue STEM-oriented education, limits generalizability. Future work should expand both sample size and diversity across multiple sites and educational backgrounds. The small sample size also forced us to use a fixed sequential modality order, with all participants completing the 2-dimensional assessment before the VR one, meaning we cannot fully disentangle modality effects from practice or training transfer. Studies should use counterbalanced or randomized assessment orders to isolate these effects. Finally, our findings are specific to the VR-MRA and MetaQuest 3, and may not generalize to other assessment tools or HMDs. Research should explore natively designed VR tasks rather than 2D translations, moving toward spatial assessments built specifically for immersive environments. That concludes my presentation. Thank you for listening. If you are interested in our work, here you can find 2 of our email addresses to contact us, plus the lab's website QR code, where you can check out our other past and ongoing projects.